Okay, we've got an example here about a bit of correlation, but mainly regression, where we have to put everything together. It's going to be wonderful. Okay, so the first thing we have to do is plot a scatter diagram of the data. All right, and although you may not have to plot an entire diagram because they don't really want to test that, you certainly could be asked to plot individual points. So make sure that you understand the scale. So on the x-axis here, we've got just one small square per unit, so anyone could do that. But on this axis, notice that 10 is actually 20 little squares, so 1 would be here. So each small square is only worth 0.5. So when I plot my first point, okay, which is an x of 5 and a y of 1.5, I'm going to have it there. Okay. So that'll be 1.5. Right, now, look, I'm going to go away and do this, but so should you. Okay, so pause the video. Don't come back till you've got a copy of this diagram. Okay, off you go. Okay, are you sure you've done that now? Okay, that's what you should have if you plot it accurately. I've been very unwise in doing it in ink, but I luckily didn't make any mistakes that time. I don't think I did anyway. There'll be a check we do to that line in just a second. Okay, so that's what your scatter plot should look like. Okay, and of course this is rubbish here because this should say x and this should say y at the very least, and really this should say time in units minutes, and this should say y, which is the temperature in degrees C. Okay, otherwise the science department will tell me off and not do my graphs properly. Right, okay, but that's the author of the booklet's problem, really. Okay, so calculate. It wants me to calculate Pearson's product moment correlation coefficient is what that stands for, and then I'm going to be getting the regression equation. So I'm going to be getting A and B. So I'll do all of that at once. Okay, in fact, you know how to do this. This was in the previous example. Go on, pause the video, lob this data in your calculator and check your results. Off you go, do that. Okay, so if you've put your data in and you've pressed option, of course it's menu item 4, and we get these values. Okay, so I've got my R. Okay, so R is 0.99964, which as soon as I saw that scatter diagram, I mean, look, this is just a perfect straight line. So I'm expecting an R astonishingly close to 1, which is what I've got. So R was 0.9996. Okay, from my calculator, and then my A and B values were A and B. Now here you've got to be a little bit careful. Okay, I've warned you about these nasty little minus signs. So the minus signs are not very conspicuous. A is minus 0.4714 and B is plus 0.40095, which is close to 0.4010. But of course the question didn't ask me what A and B were. I've got written out twice, but they didn't ask me what A and B were. They asked me what the line of regression was. Now it's kindly restated y equals a plus bx here, but of course we saw that when we went into the correct mode on our calculator. It was a menu option, so there's no excuse for getting A and B in the wrong places. So y is going to equal A, which is minus 0.4714, okay, plus B, which is 0.4010 times x. Okay, and that is my regression equation. Okay, I've got x as the value I put in, so x is the control variable, y is the response variable, because the time we think is what is determining how warm it is. That makes sense because the longer we leave the fire on, the warmer the room should get, we think. Right, so I've got to draw this line on my scatter diagram. So all I really need to draw a line is to work out 2 points. I can work out a third one as a check if I want to, but actually in this particular case all of these points should be very close to that line, so they're all my checkpoints. Okay, in fact, if I drew a line through those points, okay, then it would probably have the right equation, but let's do it properly. So let's get what we should do is choose 2 values of x a long way apart. So the top one, 50, will do very nicely. Now I've got a horrible feeling if I choose 0 I'll get a negative value, and this stupid grid doesn't go into negative values. So I'm going to choose a value of, let's say, 3 for x. So I'm going to have x values of 3 and 50, and I'm going to work out the y values for those. So in order to work out the y for different values of x, okay, all I need to do is put the x thing here as being first 3 and then 50. So there's my first one, which turns out to be that horrible fraction, which is 0.73. Okay, so y equals 0.73. In fact, 0.7, I'm going to be lucky to plot it even that accurately. And for the second one, I said I wanted to use 50. So if I change that to 50, I get 19.57, so that's 19.6. Okay, but on my diagram, okay, if I plot those points, 3, 0.7, okay, 3, 0.7, about the best I can do. 3, 0.7 is to put it there. 50, 19.6, 50, 19.6 will be there. And if I join those 2 points with a lovely straight line, okay, then lo and behold, I get a red line that goes astonishingly close to all of the points. I think this data was made up. This is just too good to be true. Okay, never mind, that's not our problem. We've drawn our scatter diagram. Okay, now for the good bit. We've got to interpret the values of A and B in the context of this question. Now, this is another template. Remember, interpreting a correlation coefficient is a bit mean because you've got to say the strength of the correlation, the direction of the correlation, you've got to mention the names of the variables, and then you've got to do it all over again saying that a high one of these is associated with a high one of these if it's positive correlation. Okay, here there is just one way to do this. So interpreting A, in terms of your theory of straight line graphs, you know that if y equals mx plus c, then this gives you the gradient and this gives you the y-intercept. Now we're doing the same thing, except instead of mx plus c, I've got a. Now that's acting like my c, plus bx. So b is acting like the m. So b is the slope and a is the intercept. And if you say that, you'll get no marks at all because that's not in context. What we've got to do is say for a, that would be the y-intercept. And it looks like it's going to be minus. So, well, firstly, we say the value of A. If you just say A is something, you won't get the marks. We've got to refer to the value of A. And the value of A we had on our previous sheet is minus 0.4714. So I'm going to talk about that number. It's it's the y-intercept, so it's a value on the y-axis. So it's the temperature. So I'm in context because I've named the variable when. Okay, so what x value have I got? Well, the y-intercept, that's when the x value is 0, and x is the time. So when the time is 0 minutes. Okay, so all you have to do to change this is change the value of the number. So if you're doing another question, then you'll have a different number and the variables may be something else. But you just say this is the y value when the name of whatever is on the x-axis is 0. You just fill these two slots here with the name of the y variable and the name of the x variable. Okay, and now interpreting B, well, B in this case was 0.4010. Now that's the slope of the line, but here this is one to learn because this may not come naturally to you, but in fact the slope of the line is when the y variable goes up by when the x variable goes up by 1. It's what the y variable increases by. So 0.0410 is it's the increase in the y variable. So I say the increase in temperature, I name the y variable, when the x variable, but in this case this is the time, when that increases by 1. So the things that change in this sentence are the number, you put in the correct value of b, and then you name the y variable, so it's the increase in the y variable when the x variable increases by 1. Now if b is negative, then you would probably not put the minus on and you'd say decrease instead of increase. But you can use those templates to interpret a and b in any regression equation. Okay, we're doing quite well with this question. We've now got to start using our regression equation. So I'm going to copy that at the top of my page from the work we did before. So this was the equation, and I've got it here to work with. And now I've got to make some predictions. So I need to make a prediction 13 minutes from switching on and 16 minutes from switching on. So this is just two different values of x to plug in. I've already done something similar working out those points. So in fact, that's when I worked out when x was 50. So I can now go back and work out when x was, the first one was 13. So when I put 13 in for x in my equation, I get a stupid fraction which equals 4.74. So 13 minutes, I'm predicting 4.74 degrees C, and for 60 minutes, okay, I'm going to change that to a 60. all right, and that's 23.6 degrees. 23.6 degrees, 3 significant figures should be fine. Okay, all right, so I've just mechanically put some values into the equation. Now I've got to comment on the validity. All right, now this is where you've got to be careful with regression, because although I had a really beautiful straight line graph, I mean, you can't get much, ask for much more than this, this graph cannot carry on being true forever. Okay, because the points are such a good fit, I would expect the prediction for 13 degrees to be absolutely spot on. Look how well the points line up. Okay, that's called interpolation, because the value 13 I'm putting in is within the range of the set of the values for which the line was established. Okay, all right, but if you think about it, as we leave this room with the fire heating the room up, the room cannot continue to get warmer at this rate, because otherwise, if I left it for years and years, the temperature in the room would be the temperature at the center of the sun, which is not going to happen. So this straight line relationship won't continue forever, and therefore going past the ends of the given set of data is an extremely dodgy thing to do, which is called extrapolation. So you need to learn these two words, interpolation and extrapolation. So I say the prediction for 13 degrees is likely to be valid, but I need to give a reason for that, and my reason is going to be because it's interpolation, and similarly my reason why the prediction for 60 minutes may well be invalid is that that would be an extrapolation. So learn these words, interpolation or extrapolation. I mean, there are other reasons why the prediction you make from one set of data may not fit another situation. Maybe it wasn't based on a random sample, or maybe you've collected data for one room and then you're trying to make a prediction about another room. There's no reason to believe that would work. So use your common sense as well. But one of the reasons why use of a regression equation may not be appropriate is extrapolation. Okay, now on to residuals. So the residuals are how far the real values are away from the predictions, and there's a formula for residuals. It's in your notes. It is essentially, what to learn is that it is the actual value minus the predicted value. So if we actually look at the graph, okay, this was a very, very good equation, but I can see, for example, this value here at 30 minutes, the actual value seems to be a little bit higher than the prediction. So this point would have a positive residual because it's actually above the line, whereas this one at 40, maybe that x is a little bit below the line. If the actual one is less than the predicted, you'll have a negative residual. So let's see that in practice. Okay. Those two values are in fact two I've got to work out. So what I need to do is calculate the predicted value at each of 20 and 30 and 40. Well, I've still got that equation that I've been using. So my predicted value for 20 will be, here we go, 7.54. So I can put that somewhere. The calculation here is the 7.54 is my predicted value, but I need to do the actual value minus the predicted value. So 7.7 minus that answer, 7.7 minus that answer is, in a useful form, plus 0.151, plus 0.1514. Okay, and then I repeat the process at 30 and 40. So if I go back to this and change the last number to 30, then I will get 11.55 is my predicted value, which is the one I need to take away, and I need to take that away from the 11.7. So I do 11.7 minus that answer, and I get 0.14 plus 0.141, and finally for 40, which I thought might have a negative residual, if I go back to this, I will delete that and I'll work out 40, and the predicted value, which I have to take away, is 15.5, and so my actual value was 14.4. So actual minus predicted gives me, actually this is 15.6. So if I do 15.4 minus that answer, 15.4 minus answer, then I get my residual is this number minus 0.17, minus 0.17. Well, let's say 69, because we've been going to 3 significant figures. Okay, so those were in the direction we predicted, so that looks all good. Okay, so we've got the residuals of all the missing pairs. Okay, does this change your view on the reliability of the predictions? Well, I'm being asked to look at residuals in the context of reliable predictions. Now, you know, really, if I look at that, and if I look at the fact the correlation was 0.9996, I don't really need to look at residuals. I can see that this line's a very good fit to the data. The idea being that if you have a picture like this, okay, where the actual data points are miles away from the line that's supposed to be predicting them, then you might say, oh, well, you know what, there's a lot of scatter in the data. It's not a very exact relationship. The correlation is far from being perfect, so I'd expect there to be significant errors. Here we can see that when the line is valid, it makes very small errors indeed. But the method that the notes suggest you use is calculate the residuals as a percentage. So, as an example, the percentage error in the residual well, let's choose a relatively large residual. So one of our bigger large residuals is this 25 degrees, 25 minutes, x equals 25 minutes. Okay, well, the residual, that tells me the error. So the residual, 0.148, okay, expressed as a percentage of the real value. So the real value for this was 9.7. So 0.148 over 9.7, the percentage error in that is, there's the calculation, there it is as a decimal, 0.0153, which is 15.3, no, so it's 1.53%, okay, so that's a very low percentage error. I mean, some people say that 15% is some kind of threshold. If you're making percentage errors of worse than that, you throw it in the bin. That's an oversimplification, but you know what? You can say that. So if you look at your percentage errors and they're quite small, say below 15%, then say, no, this is fine. So our answer to our question is the percentage error is small, so we still think the prediction, well, hang on, let's see what we do think. We thought that the prediction for 13 degrees was okay because it was interpolation. Well, we still think that, okay? But, okay, just because these residuals are small, we're still only looking at the original range of the data, so there is no reason to start thinking that the extrapolation is a valid estimate. So that's still likely to be invalid. So, I mean, the short answer is no, we haven't changed our view.